Thanks, everybody. Welcome to our next video. So we are going to be entering one of the most big parts of the course on automatic control systems, which is the analysis through the Laplace transform. Okay, so we are going to explain the Laplace transform first, and then we are going to explain uh, how do we solve a system of differential equations using Laplace transform. Now, let us begin by the basics, right? Let's say we have a model of differential equations. We may have one or more, but initially, let's say we have one differential equation describing some sort of system. Let's say it's a mass spring damper system. Okay, the classic one. So how do we analyze this? How to obtain the solution of the system? Okay, so let's say at time zero, I'm applying some force, or maybe I'm time zero, I'm just taking the mass, moving it a little bit further, and then leaving the system free to make its own transition. So, how do I obtain this solution? Well, one might say, obviously, you have a differential equation. You must have had some sort of previous course on differential equations or calculus and analysis. So you apply all your calculus knowledge and solve the differential equations, the differential equation and obtain the solution. Okay. So this is the direct approach. But one might think, okay, Lazarus, I mean, come on, I mean, this is a little bit hard, okay, even for simple differential equations. Maybe I'm not that good at calculus, and I don't remember this previous course very well. So, one might think that this approach is very direct, but also is not very practical because it requires a bit more difficult knowledge, more advanced knowledge, like calculus. And also, we can obtain the analysis, the solution of the system as it is, right? But we cannot so easily analyze the system. Okay. So this is where this indirect approach of the of the Laplace transform comes. Okay. So the idea behind the Laplace transform is this. Instead of going directly into the solution using calculus, instead we go indirectly. We first take the Laplace transform of this differential equation. Okay. And this Laplace transform will give us an algebraic equation. Okay. So first things first, okay. Instead of working with differential equations, using Laplace transform, we will end up working with algebraic equations. Much easier, right? And by performing a very simple analysis on the algebraic equation, and actually, as you will see, the analysis is on a very fundamental level. Pretty much, we are going to use tools that we have previously seen in secondary education, right? So we're going to do this sort of analysis on the algebraic equation, and then through the inverse Laplace transform, we are going to obtain the solution of the system. Okay, it's very simple to solve the system this way. Okay, so the first important pro that we gain from this is that we can easily solve the system using an approach that you will see is much simpler compared to direct calculus, right? But it's not only that. The good thing is that by using the Laplace transform, we can also perform a series of analysis of the system behavior without requiring to solve the system. Okay. So without obtaining the solution, through the Laplace transform, we can do the following. We can observe what is the system's steady state, meaning that we can understand where the system is going to end up after performing this sort of oscillation or transition. Okay. We can study the transient behavior. So we can study if the system is going to oscillate or not, and how big is the oscillation to be, for how long, and all of that. Okay. So we can analyze the behavior of the system. All right. Uh, how is it going to behave? Fast, slow, or maybe having some sort of oscillation, or not having an oscillation, and where is the final state going to be? So all of that we can analyze using the Laplace transform without solving the system. Okay, so we will be able, as you see in the next videos, to draw these kinds of graphs without solving the system explicitly. Extremely amazing feature of the Laplace transform, right? And also we're going to do some other stuff as well. For example, we're going to break down the system into possible subsystems. And you will see that no matter how big a differential equation is going to be, first order, second order, 10th order, 100th order differential equation, we can always break it down into individual terms, okay? And we can do so using the Laplace transform, okay? So we can break down very, very big systems this way, which is a great feature. And another good feature is that we can possibly study if we can simplify or maybe approximate, this is a better term, if we can probably approximate a higher order system by a lower order system, right? And this is very hard to do using differential equations, but it is much, much easier to do using Laplace transform and what we are going to see next, which is the so-called transfer function, right? So many good things are coming from using the Laplace transform over the calculus methods. Also, the good thing is this. No matter how big the differential equation, in order to solve it using Laplace transform, you only need to know some very basic properties. Okay, I think I have listed them in the next slide. So the Laplace transform, usually we have a very classic notation. We take the Laplace using L of some function x, which is a function of time, right? And the Laplace transform is usually denoted using the capital letter of the same function, okay? So the Laplace of f of t is f capital of s, right? And this function s right here is, I would simply say, is the variable not in the time domain, so it's not time. It's a variable in the frequency domain, right? And it's simple as that. You don't need to think about it any further. Of course, you might think, Lazarus, this is an integral, so we are going to solve an integrals each time. I mean, you're kidding us, right? You told us that the Laplace transform is easy. Yes, it is. So we don't need to solve integrals each time we need the Laplace transform of a function because we are going to use some very, very basic properties. Okay. And these are listed right here. So on the left, these are taken from the Nice book. Now, initially, you just need to know a couple of Laplace transforms, I'm sorry, for some very basic input signals. Okay, so uh, the impulse function has a Laplace transform of just one. The step function, which as we said is a switch on zero, has a very simple Laplace transform 1 over s. Then the ramp function, which is t times the step function, has a Laplace transform of 1 over s squared. And then as we increase, we go t squared, t to the n, all right? All the Laplace transforms have this very fixed formula, factorial n over s to the n plus 1, right? So these are the basic input signals. And then for solving differential equations, you also need to remember the formula for the exponential function. Okay, so it's the exponential starting from 0. That's why it's multiplied by the step input. And this has a very simple formula, 1 over s plus a. Now, how do we remember that? You need to think of this. What is the term here? Epsilon to the minus alpha t, right? So I will need to define a polynomial where if I set it equal to 0, right, the denominator, the solution is going to be minus a. That's why this is s plus a, because if I set this denominator equal to 0, the solution is going to be s equals minus alpha, minus a. Okay, that's why minus a goes here. So it's very easy to remember. Whatever you see right here, this is going to be the root of the polynomial in the denominator, right? And then, based on that, all other variations, which are multiplied by the factor of t, so t times epsilon to the minus a times t, we have this very simple formula. It's n factorial over s plus a to the n plus 1. Okay, it's a variation of this formula right here, which, initially looks very difficult to remember, but on the next videos, we're going to solve a couple of problems, a lot of problems actually, and you will see that these are super basic, and after a couple of examples, they are very easy to remember. Okay, so please, there is no need to panic. This seems like a lot of properties. They are not actually. They are just a couple of properties that repeat again and again and again. So after you solve like 3 or 4 or 5 exercises, they're very easy to remember. Okay. Now, some other basic properties for the Laplace transform. We have linearity. Very important to remember that. So for example, if you're taking the Laplace transform of a very big expression, this is actually going to be the summation of the Laplace transforms of each individual term, right? So just like that, this is a very interesting property. And of course, this is another interesting feature, the Laplace transform of the derivatives. I'm going to give you a lot of examples here. So let's say the Laplace transform of a function is f of s. The Laplace of its derivative is s times the Laplace minus f at time 0. Okay, so this refers to the initial condition of the function. So what's the Laplace transform of the second derivative is s squared of the Laplace minus s of the initial condition at 0 minus f of the initial condition at 0 of the derivative. So you see how it goes. For the derivative, we go towards s. For the second order derivative, we go on s squared, which then becomes s, which then becomes s to the 0, stable term. And then for the nth order differential, the nth order derivative, I'm sorry, we're going to go s to the n minus s to the n minus 1, s to the n minus 2, and so on, adding one more derivative each time. Again, this is very easy to remember. Okay. Now, the final function, the final property, which is very important, is the final value theorem. Oops, I'm sorry. The final value theorem is a simple limit right here. It's extremely useful because it tells us what is the final value of the function as time goes to infinity. So this f of infinity right here simply means f of time as time goes to infinity. Once this, of course, it has to refer to a stable function that doesn't go to infinity itself. And this is going to be extremely useful when studying examples and studying specific systems, because we can simply, compute what is the final value of the output going to be. So these are the very helpful properties for the Laplace transform. So let's see some very basic examples right here. So let's talk about this one. It's the Laplace transform of a summation. So it's going to be the summation of the individual Laplace transforms. 2 times the step input, I mean the step input. 2 times the step input is 2 over s, and plus the ramp input, which is t times the step 1. The step function is 1 over s squared, right? So simple as that. Let's see another example. Let's see. This one, okay, is 2 times the exponential function epsilon to the minus 3 times t, of course, multiplied by the step input. So this is 2 times, remember, what's the 0 here? It's minus 3, so I need to have a polynomial where the denominator is s plus 3, because if I set this to 0, the solution is going to be minus 3, which is the term right here in the exponential. Minus epsilon to the t, okay, so this is this term right here, 1 over s minus 1, because if I set this to 0, the solution is going to be s equals 1, right? So this is the exponential term right here. Simple as that. And let's see another bigger formula. We have the Laplace transform of this summation. We have 3 terms. So it's the Laplace transform of each individual term. So for the second order derivative, we have 3 times. All right, let's draw a parenthesis. Nice. So second order derivative, s squared of the Laplace minus, okay, s squared goes to s, and x of 0. So this is the initial condition of the function x, minus, this is practically s to the 0 right here, okay, minus x to the 0 of the initial condition at time 0 of the derivative, right? Then for the second term, we go towards here. We have 2 times, parentheses. This is a first order derivative. So we have s of the Laplace transform minus the initial condition of the function at 0. Nice. And then this x right here becomes x of s. So again, this is a very simple formula. We're going to solve a lot of exercises, and you will see that computing the solution of a differential equation is very easy when you use the Laplace transform. Okay, so simple as that. And on the next video, we're going to be a bit more analytical on solving systems. Any questions that you have, write them in the comments. Okay, so thank you very much.